Okay, so thank you so much for the invitation. It's really lovely to be here again. This is joint work with Roman Bezrukavnikov, Pablo, Boixeda, Alvarez, and Zhiwei. I'm really kind of plus epsilon on this project, but anyways, there's a paper which is on the archive, and I refer you to that for the kind of precise mathematical content, and I'm going to try and give a more slightly speculative, maybe slightly more physicsy overview of the project. Don't worry about this. This is grant numbers for legal compliance. So let's get started. So we're going to fix a compact Lie group G sub C. And a Riemann surface sigma. And we've already heard a little bit about moduli space of Higgs bundles, G Higgs bundles on sigma. Or we can think the moduli space of harmonic bundles, so harmonic G bundles. So this shows up as Coulomb branch of one of these class S theories. And there's a number of different interesting complex structures on this space, which go under the name of the Dalbo, Duran, and Betty complex structures. In each complex structure corresponds to a different interpretation of this moduli space. So this is Dalbo complex structure, and we're interpreting it as the moduli of G bundles, where G is the complexification of this group, plus a Higgs section. And we want to take the sort of stable such things. In the de Rham complex structure, we have again a G bundle. But instead of a Higgs section, we have a flat connection on our bundle. Again, there's a notion of stability. And in the Betty interpretation, we have a G-local system. So more or less a map from pi1 of our curve into G, modulo automorphisms. And so there's a single moduli space which parameterizes some differential geometric object, these harmonic bundles, but it has all these different algebraic interpretations, and each one gives you a different complex structure. It's called non-abelian Hodge theory.
You don't impose any sort of stability in the top level; it just comes for free, or?
Yeah, the existence of a harmonic bundle is guarantees that the underlying Higgs bundle or local system or whatever is stable. Okay, so this is it's motivational. I'm not going to go into details here, but there's a conjecture of Kapustin and Witten, which I will maybe misquote, which just basically says that this moduli space is dual in the sense of 2D mirror symmetry to the same moduli space for the Langlands dual group. And this has many consequences. And so we're going to focus on a very special case of this and on a very particular consequence of this conjecture, which will relate to the small quantum group. So basically, one feature of this duality, you might expect, would be some equivalence between the derived category of coherent sheaves on the Betti moduli space and the Fukaya category of the dual guy. So this is a so-called homological mirror symmetry. Physically, you think of these as defining the target spaces of two different two-dimensional sigma models. This is a matching of the boundary conditions of those two sigma models. Okay, and we want to focus on a kind of very, very basic example of this conjectural duality. So for us, sigma is just going to be P1. And already you should be a little bit suspicious. There are no interesting local systems on P1, but we're going to allow it to have two punctures, which is the sort of minimum number you need to have some local systems. So with the two mark points, let's say, 0 and infinity. And we're going to consider, well, moduli space of objects, which I'm just going to write, I'm going to omit sigma from the notation from now on. As follows. So again, we have a G bundle. And we have a Higgs section. But it's going to be allowed to have poles at these marked points. And in fact, we'll have a pole of order 2 at infinity, pole of order 1 at 0. Plus some extra data that I'll come back to in a minute. Okay, but basically we're looking at what you'd call wildly ramified Higgs bundles on P1. And again, from a certain perspective, this is the first non-trivial example of this kind of moduli space. In a different direction, you could consider, bundles on elliptic curves. But you might expect whatever you're doing here will be relatively computable in a rational setting. And what we'll find is a geometric realization of modules over the small quantum group in this setting. Review. Okay, so I'll get back to what that means later on, but that's the plan. What is so small quantum group means we're taking the quantum group at a root of unity, which is epsilon. And it has to be a sufficiently large root of unity, but not that big. I think bigger than the little Coxeter number or something like that. Okay. So once again, we're looking at Higgs bundles that have singularities at these two work points. And well, if you allow your bundles to have singularities, but you don't add any extra structure, then that space no longer has, for instance, a nice non-degenerate symplectic form on it. The correct thing to do, as soon as you have a tame singularity, is you add a flag at that singularity, or a complete flag fiber over 0. And at your degree 2 singularity, you want a framing of the fiber. And these both have to be compatible with this in the sense that near infinity, this guy looks like some so this is a semi-simple element of the Lie algebra, and is a pole of order 2. And then you have some higher, some less singular terms. And you want the S should be diagonalized by your framing. And you want beta at 0 to preserve the flag. Okay, so this is our data. But more or less, you should think it's a Higgs bundle with irregular singularity plus some framing data. What about the de Rham moduli space? Well, very similar. Let me not repeat all this. You can just substitute flat connection for Higgs bundle here. There's no other big surprises. What about the Betty moduli space? Well, this is, in this setting, what you associate to a flat connection is its holonomy. But if you have an irregular singularity, if your flat connection is an irregular singularity, the holonomy is not enough to recover it. This is a moduli space of Stokes data. Plus some framing. And concretely, this has a very elementary description. So this is an element of the big cell inside of G, intersected with a given orbit conjugacy class closure. Plus a flag preserved by G. So which conjugacy class? So all of these moduli spaces depend on some extra choices of parameter. So the parameters here something like the residue of theta at 0. I said preserves the flag means strictly, or I can just say with residue 0. And here we have, similarly, a kind of residue. And here we have the holonomy around 0. And so this condition, you're allowed to vary these parameters. You can pick the residue to be whatever we like. We're going to eventually fix it to be equal to 0. And we're going to eventually fix this lambda to be either unitary or unipotent. Yes.
Don't put these 2 points on there.
Yeah.
There's some sort of growth-unique theorem which will run fast throughout.
Right.
And so when you put these 2 points, can you say something about? I mean, with this condition, can you say something more concrete about the modular space, or?
I mean, it's going to be. Yeah. So there's something I'm sweeping under the rug here. This moduli space will contain representatives of all of those, well, all the classes allowed by the choice of group G. So it's actually not of finite type. So this is, I'll draw a picture of the SL2 case. This is the correct sort of diffeomorphic Betty moduli space is really the universal cover of this guy. But I don't want to get into that. Let me draw a picture. Yeah. So picture. So for Mdal SL2, this is actually relatively simple. So this is a fibration called the Hitchin fibration down to A1 or C. And the generic fiber is just a copy of C star. And the special fiber over 0, well, let's say over the distinguished point of C, is an infinite union of P1s. We'll later see it's an example of an affine Springer fiber. On the other hand, this is what? Well, it's going to be something like the, you know, you take the locus of unipotent elements and you resolve it because of Springer resolution. So you resolve it by a choice flag compatible with your unipotent element. And then you take an open subset of that by intersecting with the open cell, the big B minus B plus. And we're not really going to use the de Rham moduli space. So, okay. All right, so we have this homological mirror symmetry equivalence. The so-called B side, meaning the coherent side. This category we're interested in has been well studied before. So we're going to look at coherent sheaves on this Betty moduli space. But we're only interested, well, we're gonna limit our sites to kind of proper sheaves. So those coherent sheaves with proper support. Okay, we'll start with those. Maybe they're a bit easier. And the Betty moduli space fibers over an affine variety where you just forget the flag. Right, so you map down from the Springer resolution to the unipotent locus. And since that guy's affine, the support of a proper sheaf is just going to be some collection of points here. And let's just limit ourselves to sheaves supported on the most interesting fiber of this guy. So the sort of fiber over the identity, set theoretically supported. That's some kind of block of this category. And this is equivalent to just sheaves on the Springer resolution supported on the zero section. That theoretically supported on the zero section. So this fiber over the identity is a copy of the flag variety in here. And if you look at sheaves supported in a formal neighborhood of that flag variety, it looks like sheaves supported in a formal neighborhood of the zero section inside n tilde. Remember, n tilde is cotangent bundle of the flag variety. Sorry, that should have a coherent. Okay, so why is this category, why has it been studied? Well, one reason is its relationship with the quantum group. So this work of Bezrukavnikov, I misspell some of these names. I forgot to write them down before giving this talk. So I apologize to any of the authors if they're watching this, the unlikely event that they're watching this. So okay, so various people have studied this category and shown that it's equivalent to category of modules over the, there's T here, we're going to take T equivariant coherent sheaves, category of modules over the small quantum group associated to G. So really, these authors work in characteristic P, and they show the analogous result for characteristic P Lie algebra of G. And these authors work with the small quantum group itself, and those two theories are equivalent for a large enough frame. I don't want to go into the details of this small quantum group because it will play almost no role in this talk. But if you're curious about it, I'm happy to say limited things I know afterwards. Let me just give a very, very brief sketch of what this is. So you start with your Lie algebra G, and then you take its universal enveloping algebra. Universal enveloping algebra. Okay. And this is a kind of deformation of the quantum group. introduced by, yes, independently by Drinfeld and Jimbo. And this deformation originally was introduced over a formal parameter, but there's a version, catch the Concini, I guess, where this parameter is not formal, meaning you're allowed to specialize it to numbers. And so we specialize Q to some root of unity. If you specialize to a generic number, you get an interesting group, but as an algebra, let's say, it looks very much like the enveloping algebra. But if you specialize to a root of unity, you get something completely different. In particular, it's much more commutative than this guy. It's almost a commutative algebra. So this is finite over its center. So this thing has a huge center at a root of unity, and this is some kind of non-commutative finite extension. And what is a small quantum group? Well, it's small, it's written with a small u, self-explanatory. But this is some kind of quotient of this big guy by some central character. So if you have a big commutative algebra and you want to focus on the sort of non-commutative stuff, well, you might as well just fix a central character of that center and work with the quotient. Okay? This dot means graded modules. It's related to the presence of this T here. Okay, if you don't know anything about the small quantum group, I'm not going to tell you any more in this talk, but ask me afterwards. And if you do, hopefully, you already know all this. What is what? Oh, yes, sorry. So this algebra, we quotient by we quotient by some of the center, and then O hat tells you how to quotient by the rest of the center. Okay, and maybe just to say a word about the proof for this equivalence, it's more or less analogous to localization of category O over the flag variety. So you kind of realize the quantum group as some algebra of operators on this space here, and you localize. But because you have a large center, instead of getting D modules, you get coherent sheaves. Okay, but that's sort of previous work on the B side, and now we want to understand the A side. And maybe why do we want to understand the A side? One reason, this is a category of modules over some algebra. It has a natural T structure. This is coherent sheaves over some variety. It has a natural T structure, but the T structures do not match under this equivalence. So if you transport this T structure, the natural T structure here, to the left-hand side, you get what's called an exotic T structure, which just means it's not the usual one. You really get a family of them. For instance, it has finitely many simple objects. Certainly not true of coherent sheaves. And we'd like to understand this exotic T structure in a more geometric way. So we'd like some model of small quantum group, which is geometric, but where the T structure is kind of obvious. And that's what we're going to get, more or less. Okay. So what about the A side? Yes. Yeah, so we're looking at things that are set theoretically supported on B, the flag variety. Flag variety is proper. And so yes, all of these objects are going to be properly supported. Yeah. Yeah, this is a finite dimensional algebra, this thing. So okay. So what about the A side? So normally, A side would be the Fukaya category of embedding. And we'll get to some version of the Fukaya category, but we won't start there. So first we're going to replace. So instead of embedding, we'll consider Dolbo, G dual. This is a moduli space of Higgs bundles. And we want to present it a certain way. So here's P1, 0 and infinity. So we can trivialize our G bundle on a disk around 0, a formal disk, rather on a punctured disk. So we can trivialize it on a disk around 0 and on the complement of 0. And when we compare, we get a loop inside of our group. Compare these two trivializations. And now, if we remember, we had a flag here. So what we do is we're going to quotient the space of loops by the subgroup I of gauge transformations on the disk that preserve that flag. Called the Iwahori subgroup. This is called the affine flag variety. And this is a certain quotient of the affine flag variety, or rather of its cotangent bundle. By a certain infinite dimensional group. So what's this guy? This is gauge transformations on the complement of 0 that specialize to the identity. Maybe I'll write it this way. So the subgroup that preserves the framing at infinity. Okay, so this kind of presentation, the symplectic quotient, is well, it's not hard. Given it's a relatively intuitive presentation. You're just saying we trivialize your bundle away from infinity and, sorry, away from 0 and at 0. Compare the two trivializations and then quotient by the extra choices that you made. And you get this presentation. So this is a big infinite dimensional space. But we're going to start by thinking of our A side as a sort of equivariant sheaves on this space. And I said it's a symplectic reduction at some, but not at the 0 value of the moment map, at the value psi of the moment map. So this is mu inverse of psi minus, where psi is basically, I erased it now, but it's the choice of leading order term of our pole at infinity. So near infinity, we fix some behavior of our Higgs section, and that specifies a character of this group. So minus to C. And we can take the fiber of that character. Okay. All right. So now I want to do something. So we're going to pass from this infinite dimensional picture to a slightly more finite dimensional picture. We do this quotient in stages. So first we quotient by the kernel of psi. We'll call P psi at the 0 fiber of the moment map. And then we quotient by the sort of residual action of GA. Okay. And so we'll call this bun G sigma psi. So it's a moduli space, or rather cotangent bundle of this. It's a moduli space of G bundles with some sort of level structure specified by psi. And now we're taking a further quotient by GA. And so the idea is more or less that we're going to, our A side will be something like sheaves on this bun G. But not quite. Okay. So maybe let me step back and look at a more general situation. So supposing you have a group like, let's say, GA acting on some space N, then sheaves on N, if GA acts freely, let's say, simplest case, you take the quotient by 0 at the 0 value of the moment map, then this is something like GA equivariant sheaves on N itself. And so you can take the quotient, or you can consider covariant sheaves. Here we're taking a quotient of the non-zero value of the moment map, so we have to do something a little bit weirder. So recall that we had our space, our underlying curve is P1 with 2 marked points. There's an action of C star just rotating P1. And one of the reasons this moduli space is so nice is that this action will induce, if you do it properly, an action on the moduli of Higgs bundles, fixing this singular data. Okay. So this is not generally the case if you have curves with punctures and irregular singularities. It's not generally the case that you have a C star action on the moduli space of Higgs bundles. But in this very simple situation, where you're working with P1, you can arrange that. Okay, and so not only does C star act on this elbow space, but it also, I mean, it acts on this entire structure. In particular, it acts on this funny moduli space of G bundles with level structure. And this action is compatible with the action of GA in the sense that really you have an action of a semi-direct product. Yeah, semi-direct product of these two guys where C star acts in the usual way on GA. So in this context, you can define something called the Kirillov category. Kirillov of. So what is this? This is just a derived category of sheaves that are C star equivariant on this on G, modulo category of sheaves that are GA cross C star equivariant. And you can convince yourself that this is the correct replacement for this in the situation when you're quotienting by a non-zero value, taking a non-zero value of the moment map. So so slightly confusing setup, but let's just summarize by saying that our A side category is going to be a subcategory here. So our A side of this Kirillov category. So what is a subcategory? Well, given any sheaf on a space N, you can associate its singular support, which is a subset, a conical subset of the cotangent bundle, closed conical subset. If your sheaf is constructible, this is going to be some singular Lagrangian. And it captures basically the directions in which your sheaf has singularities, in which its stock jumps. Okay, this is called the singular support. And so we want to limit the singular support of our Kirillov sheaves. And so we consider the Hitchin fibration from our Dolbeault space down to CR. So this is the thing that takes Higgs bundle to its spectral curve. And again, we have this C star action on this space, and the C star action passes to the base of the Hitchin fibration and has a unique, it contracts it to a unique fixed point, the origin. And the fiber over this fixed point is a retract of this space, more or less. We believe that to be true, and the inclusion induces an isomorphism on cohomology. So this is the singular Lagrangian retract of the full Dolbeault space. Put a star here because this is not something we've proven. And for those who know, it's homeomorphic to an affine Springer fiber. Homeomorphic to the affine Springer fiber over psi in the affine flag variety of G. I won't explain what affine Springer fibers are. But in our SL2 example, that would have been this central fiber here, an infinite chain of P1s. And so we'll call this guy lambda for Lagrangian sub psi. And we're going to consider the Kirillov lambda psi inside this Kirillov category. So objects with singular support. Lambda psi. And we add a finiteness condition, so supported on finitely many components. So you imagine an object supported on finitely many of these P1s. Okay, and so I can now state the main theorem. So we have an equivalence between the derived category of this guy and the B-side category for the dual space. So you write that as embedded, such that the exotic T structure here is matched with the perverse T structure, so the natural T structure on this side. Okay. Yes. So it's a little bit hidden. If you impose a singular support condition, a Lagrangian singular support condition, that kind of forces your sheaves to be smooth with respect to stratification. The stratification has to do with, well, first of all, if you recall, yeah, it's it's a little bit hard to say. So there's an open subset which just looks like G mod B inside this bun G, and then you have, well, infinitely many smaller strata, an infinite type thing. Yeah, maybe let me afterwards I can try to give a better answer, but it's okay. So let me try and, so this maybe this slide looks a little bit mysterious. Let me try and give a conjectural translation of this into something maybe more familiar to the physicists. So for now, you can see this is this is in the spirit of geometric Langlands. You have some category of, constructible sheaves on one side, coherent sheaves on the other side. They're equivalent to each other. So a version of Betty geometric Langlands in the wild setting. And I want to make this look more like mirror symmetry, two-dimensional mirror symmetry. So Shiwara and Shapira developed this notion of microlocalization. Well, sorry, I guess that's maybe originally due to Saito, but this developed a kind of microlocal sheaf category formalism. The basic idea is the following. So you consider a subset of the tangent bundle of some manifold n, open subset. And you can define microlocal sheaves on this subset, I'll put a pre here, to be just sheaves on n modulo sheaves that have singular support on the complement of this subset. So singular support of f is contained in T star n minus omega. So you're just killing everything whose singular support is doesn't intersect omega. And this defines a sheaf of categories, well, a pre-sheaf of categories on the cotangent bundle. So it's a kind of localizes category of sheaves to the cotangent bundle of a space, hence the word microlocal. And given a pre-sheaf of categories, you can sheafify it. And so this is a sort of sheafification of Heshiwara Shapira's pre-sheaf. This is something that they would presumably have done had they had access to modern infinity categorical technology, but their work was produced before that. And so you get some sort of sheaf of categories on the cotangent bundle that localizes dBn. And we can apply this to our Kirillov category. So you can look at Kirillov sheaves, the spongy. And we microlocalize. And you get some kind of sheaf of categories. In the cotangent bundle of, well, a sheaf of categories along this lambda psi. This is the affine Springer fiber inside the cotangent bundle. Yes. Yes. What do you use for gluing? Well, you're not somehow to each open set, I've associated some kind of triangulated category, right? Now, if you instead you take the whatever DG enhancement of this triangulated category, you get some pre-sheaf of DG categories over T star n. And I mean, I don't pretend to be an expert in these things, so I'm probably not saying this entirely right. But basically, you there's some kind of somewhat general nonsense method to produce an actual sheaf of DG categories or infinity categories from this pre-sheaf data. In this, more or less in the same way you produce a sheaf from a sheaf of abelian groups from a pre-sheaf of abelian groups. And you just take some limits. But of course, the output is difficult to control in general. You don't necessarily know what this looks like. But yeah. Okay, but I just want to quickly say, so this is not a surjective functor, but we can show it's fully faithful. Oh, sorry, we can show it's fully faithful. We believe we know it's surjective onto a certain explicit subcategory here. And this, by work of Ganatra, Hardin, and Shende, plus some extra work to be done. This is equivalent to the Fukaya category. Sorry. Yeah. This is equivalent to the Fukaya category. The Stalbo dual. Okay. And so composing our equivalence with this kind of microlocalization functor, you get a functor from coherent sheaves in the Fukaya category. And so conjecturally, you can drop the properness restrictions. You can drop the support conditions. And you really should get a full equivalence between the Fukaya category on one side and the coherent sheaves on the other side. What this gives you is an equivalence between the sort of subcategory here, the coherent sheaves supported on the flag variety, mapping into some subcategory here. Okay, so this is somehow our result. Okay, so maybe I'll stop here. Thanks for listening.